Hi, it's a pleasure to record this presentation for Indo-German Frontiers of Engineering Symposia. We are participating in this symposia for the first time, and we are really excited to present our work in the symposia. Our group is a very recent group at Indian Institute of Technology, Delhi. We are working in catalysis for renewable energy and chemicals research. We are applying both theory and experiments, starting with density functional theory simulations of materials and mechanistic explorations leading to ab initio microkinetic modeling. We are testing all of this with proof of concept experiments in our lab. Recent interest is on machine learning approaches and how to make things faster. Applications vary a lot, starting from biorenewable platform chemicals to natural gas chemistry, electrochemistry related to solid oxide fuel cells and battery materials, traditional catalysis like alkanes to olefins on zeolite materials, and some recent interest also is there in CO2 conversions to useful chemicals. Let me briefly highlight some of the work which is done in past. We have been focused on one area which is related to catalysis in complex reaction environments, understanding the role of biogenic impurities at the fundamental level, designing new platform chemicals which are derived from fermentation and can be valorized to high value fuels and chemicals. We are applying ab initio microkinetic modeling to design bimetallic surfaces to obtain high product yield with high selectivity. Uh, this is further combined with, as I said, with machine learning approaches to increase or to speed up the process. We have been fabricating nanostructured thin film electrodes for solid oxide fuel cells, where we have identified cation segregation to the electrode surface as a rate limiting process. And we are designing new strategies of fabricating electrode materials which can overcome these limitations. On the natural gas chemistry, we are focused on understanding the active sites in this chemistry and how you can stabilize the active sites by tuning experimental protocols which can give high product yield with highly stable catalyst materials. The core idea in our work lies in the rational design of a heterogeneous catalyst, where we are looking at specific sites, for example, how to alloy materials at different facets, how to look for different selectivity coming out from different facets in a catalyst, what is the role of the step sites, what is the role of the corner sites, and what is the role of the terrace sites in overall catalysis. We are really interested in understanding not just where is the active sites, but what is actually the nature of the active sites and how active sites are evolved in heterogeneous catalysis. For example, in methane dehydroaromatization reaction, we are looking for an ensemble average representation of active sites and reaction rates expressions which can capture this ensemble average representation. So not just the most or the lowest energy structures of the active sites, but we are also looking for the metastable species or the metastable structures of the active sites which are contributing in the reaction rates. This is trying to represent the overall reaction rates as a wholesome representation which can probably address some of the fundamental understanding in catalysis. To know more about our work, please visit our webpage at hariclab.in. I really appreciate your time in listening to our work. Thank you very much.